So we've written some classes that use a singly linked list and a doubly linked list to implement mutable collections. And we specifically had them extend the buffer trait because that is kind of the general mutable sequence in Scala. But the linked list you use the most in Scala is actually an immutable linked list. Turns out that the list type is an immutable singly linked list. And now, turns out that when you make an immutable list, it needs to be singly linked. So this is what our linked list looked like before. We have a head, we have a tail, and we have a bunch of nodes, and in some ways all of those are encapsulated inside of a list type. If we were to look at our code for this, we had the node type, we had our head, we had a tail, and we kept track of a number of elements. When you make your linked list immutable, you fundamentally change in how you do a number of things with it. One, you don't keep track of a tail because it turns out you don't really use it. Two, it turns out that instead of having a node type that is inside of your class, you actually just use the class itself becomes the node. And it generally doesn't store a length because that winds up being kind of superfluous information. Instead, when you want the length, you have to actually walk the list. So let's look at how this, we're going to implement one of these, and we're going to make it so that it extends the type Scala collection immutable linear sequence. So you might remember from a number of playlists ago, we looked at the Scala collections in general, and a linear sequence is a sequence that is potentially slow to access the individual elements. Generally, when you use a linear sequence, you have to take order in time to get to the nth element. And it says here, linear sequences have are reasonably efficient for head, tail, and is empty, but some of the other methods could be slower. In particular, they might take order in time to work. And we have to have an apply and a length, and then we get a whole bunch of other things here when we do that. Though we generally want to override some of the other implementations to make them more efficient. Okay, so let's go ahead and we're going to create a new, I'm actually going to make this a trait, an immutable SL list. That way it matches the mutable SL list that we wrote previously, being consistent in our naming conventions. And we'll start off, so we'll say it's of type A, and it extends linear sequence of A. Now it turns out there's multiple linear sequences. There's the generic one, there's the immutable one, there's the mutable one. So I'm going to go ahead and I'm going to import collection.immutable.linear sequence to make it clear which one we are doing here. I'm going to do something else that we haven't played much with, and that is I'm going to make this a sealed trait. And what sealed does, again, is it prevents you from having any subtypes that aren't in this file. So all subtypes of this will have to be inside of this file, and that way people can't create things that we didn't want them to, that will be subtypes of this. Okay, that's a reasonably good starting point. So for the linear sequence, because it's a linear sequence, we got a number of different methods here. There's a head, there's a tail. We know that we have to write the apply method, we have to write the length method. But I mentioned earlier that the immutable linked list doesn't have like an object that encapsulates head and tail and the nodes. Instead, it is the node. Okay, and so we're actually going to make two subtypes of our immutable SL list here. One of them, and I'm actually going to make both of these into final classes. Remember, final means that you can't extend it. So this is kind of the end of the line here. One of them is going to be called cons. And you might remember that cons is how we read this colon operator, and there's actually, that's why I'm naming it this. So cons on type A is going to take a val for the first value in the list, head, which is of type A, and then it will also take a val for the rest of the list, which is an immutable SL list of type A. And of course, I want this to extend my type up here on A. So this is basically a node that keeps track of a head and a tail. Okay. And we need to put some of these methods inside of here, because I'm going to start getting errors. One thing you'll note, this says that it needs to override. And we're going to have to do the same for tail. Now, we haven't really seen this much where we're overriding a val. Well, this is one of the things that Scala allows you to do, is you can override a def with a val if it's just something that's set and isn't going to change, so it doesn't need to be reevaluated. Now, this is unhappy because as a class it needs both apply and length from the linear sequence up here. So we're definitely going to have to implement our length. We are definitely going to have to implement the apply method, which gives back something of type A. And for efficiency, it's actually good to override the isEmpty method. And it turns out this one is really easy. A con cell is never empty because it always has a head value followed by the rest of the list. Okay. Now this actually compiles. But it's not functional yet because this is a cell that represents a value followed by the stuff after it, which could be another con cell with a value and stuff after it. Could be a con cell. At some point you have to stop. Okay, and for this, we need to have another type that represents basically what for a list is nil. So I'm going to call it myNil. And first, I'm going to make it so myNil has type A, extends our immutable SL list of type A, yeah. Because a con cell has to have a type following it that is of the same type. Okay, what about here? Well, turns out the implementations here are fairly easy. Length is 0. Def, an apply method, index of int, well, there's nothing here. So this throws new illegal argument, exception, can't index nil. Something like that. P-T-I-O-N. Did I manage to spell it right? Nope, I have an extra E there too. There we go. Okay, so those are basic implementations of that. Just to have these things be complete, override def is empty is true because the nil is always empty. Override def head, and then I'm actually going to do the same thing for tail, are also going to throw exceptions. Can't get the head of nil, and we'll do the same thing for tail. Okay. Length. Let's go back up to here and let's implement this a little bit. So what is length going to do? Well, length is this element plus the length of the tail. So it winds up actually being a recursive definition that runs through and goes to each element and then adds them all up. And of course, the last element is always nil, so it gives back 0. Apply. Well, if we're asking for an index of 0, that would just be the head. What if we're asking for an index that's not 0? Well, if we're indexing for an index not 0, it's somewhere in tail. We don't know where it is in tail, but we could make tail look it up. And so we could have tail look up the index of n minus 1, because we've skipped the head here. Oh, and I called it n instead of index. Okay. So we have these implemented. This isn't quite functional enough for us to use it yet, and it turns out there's an extra little thing that we want to do. One of my problems right now is I have to make, if I want to make an immutable singly linked list of int, it has its own version of nil. So I would have a nil for ints, I would have a nil for strings, I would have a nil for everything. I don't want to do that. Okay, and so we actually have to introduce another language feature in order to make it so we can have one nil that works for all lists. So we'll come back in the next video and we'll talk about how we're going to do that, and then we'll finish it off and get it to the point where we can actually work with this code.